We're going to start off looking at diodes. A diode is a kind of component which is made from a semiconducting material such as silicon. This is the diode and this is what its symbol looks like. It's like an arrow. Diodes have this unique property of only allowing current to pass through them in one direction. The arrowhead on the symbol shows the direction of the current flow. Some diodes emit light when they conduct electricity. These are called light emitting diodes, or LEDs. We're going to change the value of the voltage and see what happens to the current. So as we increase the value of the resistor, when the potential difference is 0.2 volts, the current is 0. When it's 0.4 volts, the current is 0. 0.6, there's a little bit of current. 0.8 volts, the current is 0.3 amps. 1 volt, it is now 1 amp. So suddenly there's a big flow of current. If we change it the other direction, let's swap the battery round. The voltage, a potential difference of negative 0.0 volts gives no current. 0.2 volts gives no current. 0.4 gives no current. 0.6 volts across the diode gives no current. 0.8 volts across the diode gives no current, and so on. So if we plot the graph of voltage against current for the diode, these are the values that we had. We'll press play. So now we're going to basically plot the graph of potential difference across current. For all the negative values of the voltage, there's going to be no current. You notice that suddenly the current starts to flow after about 0.6 volts. So with a negative potential difference across the diode, no current will flow. So the resistance in the reverse direction is high. And the diode switches on with a potential difference across of about 0.6 volts. With a large potential difference across the diode, then current will flow quite smoothly. The resistance is very low in the forward direction. Now, for materials to conduct electricity, they must be able to transfer a charge when a potential difference is applied across them. Metals conduct electricity due to these delocalized electrons. These electrons are not bound to a single atom, but act as a source of mobile negative charge. Despite the free charge, metals have a net neutral charge. As free electrons are released from the metal atoms, the atoms are left with a balancing positive charge. Some semiconductors also contain a pool of delocalized electrons which allow the current to flow. However, semiconductors can also contain groups of atoms with an unusually low number of electrons. These regions are called holes. Holes are positively charged. They are able to flow through a semiconductor just like delocalized electrons, but in the other direction. Similarly, their formation leaves an opposing fixed charge behind. Semiconductive materials can be artificially modified to adjust their conductive properties, adding extra holes or electrons to their structure. So a diode is a one-way gate in a circuit, and diodes are made of semiconductors such as silicon. So let's look at stage 1. The silicon diodes have two distinct regions, one with holes, called the P side, positive, and one with delocalized electrons, called the N side, which is negative. Overall, of course, they're neutral. The diode has a net neutral charge. The holes and the electrons on each side of the diode are balanced by an equal and opposite static charge. When there is no potential difference across the diode, the free electrons and holes attract each other. Some electrons and holes meet and they neutralize each other and they form a depletion region between them. The depletion region lacks free charge. The remaining static charge is no longer balanced, creating a charged region. This repels any free electrons and holes that attempt to cross to the opposite side, so as it stands it will not conduct. When a potential difference is applied across the diode, the free charge moves. Delocalized electrons are attracted to the positive terminal of the power supply, and the holes are attracted to the negative terminal. If the negative terminal contacts the P side and the positive terminal the N side, the diode is in reverse bias. This depletion region expands and no current can flow. However, if the negative terminal contacts the N side and the positive terminal contacts the P side, the diode is in forward bias. Free charge moves towards the center of the diode. If the voltage across the diode is greater than 0.6 volts, the repulsion in the depletion region is overcome. The holes and electrons move towards opposing poles, allowing current to flow. The main thing that we need to know is that you need to recognize this graph, that when we have a forward bias, we have a current that flows. When we have a reverse bias, the current is zero, which means the resistance is very large.